Good morning, my dear students. Last session, we have completed this continuous beam with overhangs. We are in moment distribution method, unit 4 of your syllabus. So continuous beam with overhangs is being discussed with an example. So I'll just quickly run through. And now, in this session, we will talk about the continuous beams with sinking of supports. Okay, so in a moment distribution method, how we deal a continuous beam if you have support sinking. Okay, let's see what are the changes that are to be made in the procedure. Okay, so let us consider a beam AB where end A and end B are fixed. So you take a fixed beam. If the right hand side support is sinking by an amount of delta. Okay, so what is going to happen possibility is that the moments that are being developed because of this sinking effect are moment at A, it is going to be anti-clockwise moment, and there will be moment developed at B also in the same direction. So it is also anti-clockwise. So do remember, if the right hand side support sinking, then the moments developed at A and B will be in anti-clockwise direction. Okay, and the value is 6 EI delta by L square. So 6 times EI, flexural rigidity of the beam, delta, the value of sinking, or else you can simply say the level difference between A and B, and L is the span of that portion AB. Okay, so if this is for right hand side support sinking. Okay, it similarly, if left hand support sinks by an amount of delta that you can see in the diagram here, this will show you that. So the moments are developed in the direction clockwise. This is the moment developed at A. Similarly, moment developed at B. So clockwise moments. The value being same, 6 EI delta by L square. So left hand support sinks, then the moments developed are clockwise. So for moment distribution method, we are following the sign convention as clockwise positive and anti-clockwise negative. Okay, so when a right hand side support sinks, you are going to get negative moments of the value 6 EI delta by L square, and if it is left hand side support sinks, you are going to get clockwise moments, which are nothing but positive moments. So fixed end moments due to support settlements are to be added to fixed end moments due to loads. This is the change in the analysis procedure of moment distribution method, and rest of the analysis is same. So only the step 1 that you are going to do in this method, that is finding fixed end moments. So this is the only change that you are going to have. So when you calculate fixed end moments in moment distribution method, so you are going to calculate fixed end moments due to loads. Okay, so I just give a suffix L. Similarly, you are going to add or deduct according to their sign convention uh, fixed end moments due to sinking, that you are going to get final fixed end moments. That is the only change in the procedure. Rest of the analysis is same. Like step 2, you are going to calculate distribution factors for all the members. And similarly, the next step, step 3, you are going to proceed for distribution process, like uh, by taking each joint and balancing the joint, then taking the carryover moments. Then again, if the joint is balanced, if the joint balance is disturbed by the carryover moment from the adjoining joints, again you are going to balance it and carry over that moment to the far ends. This cycling is like you are going to carry out in the same way as done for the earlier cases. So the only change, if you have syncing in support, is step 1. That means you are going to add the fixed end moments due to syncing, that is 6ei delta by L square values to the fixed end moments due to the given loads. Okay, so this is what is the possible change in the procedure. Okay, rest of the thing is same. So just try this example and try to submit this as an assignment question. Okay, so analyze the beam shown by moment distribution method. Support B sinks by 10 mm. This one. Support B sinks by 10 mm, and whereas Young's modulus value 200 gigapascal. Moment of inertia is same throughout, and the value is 4000 into 10 power 4 mm power 4. Draw BMD and SFT. So this question is in fact from 2017 October, which is given for 16 marks in JNTU UK. Right. So take this question and submit this solution as assignment. Right. Okay. So as I said, support B is sinking by 10 mm. The rest of you have to change the step 1 analysis. That means calculating fixed end moments. Then remaining 2 steps like finding distribution factors and finding the distribution process to continue. It is similar, right? Okay, right. We'll go for the next category. So portal frames. So we have done with the continuous beams with all the possible changes, like continuous beam with fixed ends is the fundamental case taken, and then we have gone for continuous beam with hinge ends, and similarly continuous beam with overhang portions, and then similarly continuous beams with support sinking cases. So all possible cases of continuous beams have been done. Now the portal frame, uh, uh, next going for the frames. So two-dimensional frames are the possible frames for manual calculations. So hence we take only two-dimensional frames. So there are two cases in the portal frames. Like one is without sway and with sway. Okay. So the lateral deformation of the frame is called sway. So if the frame is not having sway, how do we solve the problem? And if the frame is having sway, how do you deal or how do you analyze the frame using moment distribution method? Okay. So let's see what about the procedure for analyzing frame without sway. Okay, so it says the analysis of rigid frames by moment distribution method is very similar to that of continuous beams, no change. So step 1, step 2, step 3, whatever are being told for continuous beam are to be followed in toto, right? So as pointed out earlier, in the case of continuous beams at a joint, only two members meet, whereas in case of rigid frames, two or more than two members, there is a possibility for at a joint. Okay. So take this example. Analyze the portal frame by moment distribution method. Draw BMD. Sketch the deflected shape. Also, the two columns AB and CD are having it's like abnormal here, 54 meters height. So just take this as uh, uh, maybe 4 meters height with I as moment of inertia. Beam, treat this as 4 meters. So there's a mistake there. It is in October 2018, right? Maybe the typographical error, right? Beam BC of span 5 meters with 2I. The beam BC carries UDL 15 kilonewton per meter and supports A and D are fixed. So again, take this as an assignment question. Submit this as an assignment problem. Add this problem to the earlier assignment question. Okay. So there are two problems now for the assignment. So BC, A, B, C, D. So AB and CD has got 4 meters height. We're taking this as 4-meter height. And beam BC having span 5 meters. So this is I for the column and 2I for the span beam. Moment of inertias are being given. Right. The BC carries a load of 15 kilonewton per meter UDL. So let's take that load. Right. So this is the given question. Draw now BMD is the question. So it's like a portal frame, but if you can just imagine that this is going to be I'm just drawing an equivalent diagram for the analysis purpose. That this is the way that we take it. Just a continuous support assumed. Just an equivalent diagram. So AB no load. CD also no load. Only BC has got UDL. Okay. So it's like a continuous beam with fixed ends, having load on BC only. So you have to treat this in the same way. As I said, the analysis is very similar to that of continuous beams because there is no sway here because the frame is symmetric about its centroidal line. Right. So about centered is symmetric, hence you don't have sway. So the horizontal movement of the frame is not possible here because columns are having same height and load is uniform to the either side of the center. Okay, and all the properties are very similar from to the left and to the right of this midpoint. Okay, hence it is symmetric. So you have to just take this as just a continuous beam, then analyze it. So it's 5 meters, like 2i, I. Okay, so just very similar to that continuous beam with fixed supports, right? So this is also try as your assignment question. Okay, so any frame without sway is to be dealt just like the continuous beam. Okay, right. So going for the other case, what if the frames are having sway? So when do you expect sway? Just like I was telling that the frame, if it is symmetric, you don't get sway. So any unsymmetry, any unsymmetry, load unsymmetry, geometric unsymmetry, like any unsymmetry can cause the sway to the frame. Okay, so how do you deal the sway frames? Okay, so the procedure is just being given. We will just discuss the procedure, then we'll practice a problem here. So assume sway in the frame is prevented by an external support at beam level. Okay, so assume sway in the frame is prevented by an external support. Carry out moment distribution process. So as you prevented sway means what? You are making the frame to not to sway, so not to move laterally. Hence we call it as non-sway analysis. Okay. How do you make that one to not to sway in the lateral direction, not to move in the lateral direction, not to deform in the lateral direction is by assuming one support at beam level. Next what? After the analysis, that's non-sway analysis, consider FBD of columns. Okay, you mean take free body diagrams of columns only. Calculate horizontal forces developed at supports. Calculate horizontal forces developed at supports, considering horizontal equilibrium of total frame. Okay, so solve for sway force developed at the support assumed. So find this S value. What is S? It is the support reaction at which you have assumed a support for stopping the sway. Okay, then what? After finding S value, assume arbitrary end moments due to sway. So now you have to see that the frame is in sway, then assume some moments because of sway. There are some moments developed, so carry out moment distribution again. Okay, so once the analysis is done, then again in the same way of finding S, now also you find S value, that you call it as S dash. Okay, that's called arbitrary sway force. Okay, because what, you have assumed some moments because of sway, you don't know how much the frame is going to sway. If you know the sway value, then you can calculate the moments exactly. Okay, so arbitrary moments you assumed, hence you will get arbitrary sway force, right? So to get the correct sway moments, then you find out correction factor, sway correction factor. What is that value? S divided by S dash. Okay, now what? how to get final end moments. So non-sway moments plus correction factor multiplied by sway moments will give you final end moments. In a simple manner, I'll just tell you that if you have a frame of something unsymmetric, something like this, okay. So you have some loads acting on this frame, let us say, something like this, okay, right? So this frame is going to have sway, okay. So in the frame, moments will be developed due to the loads and the sway, both, okay. So now what we are doing, we are separating these two and finding them separately, okay. So because of loads means arresting sway, and I'm trying to find out the moments developed due to only the given loads. Then what, I'm taking sway alone, and I'm not taking any loads when I take sway, okay, only sway, and I'll find moments, I'll add both, okay. Non-sway moments, in the sense these moments are due to given loads alone. This is only due to sway. So principle of superposition again. So we have both loads as well as sway. So loads will develop moments in the frame, and sway also develop moments in the frame. So we are going to find out two things separately. Then we add them according to their sign. Hence, will give you final end moments. This way, you can make it simple for the moment distribution method procedure, right? So this is how we deal with sway frames, right? Next session we will take an example, this one, right? Okay, thank you.